In today's lecture, we're going to discuss an overarching aspect of all instrumental methods, and that is noise. Now, of course, when you're running an instrumental method, what you're looking for is signal. However, all instruments, have got signal, as with noise, as part of it. And so that's one of the reasons, obviously, why your measurements are never completely perfect. And that's why I really insist, that every time you do an analysis, your signal, which of course should be proportional to your concentration, must always have, a standard deviation, because every measurement, is imperfect, and as such, it has some level of randomness or precision that needs to be, quantified in form of standard deviation. Of course, the other reason, why measurements are imperfect, is because of analysts' error. But as you guys, continue to gain skill, on the bench and so on, I think analyst error should always be mitigated and very much, reduced. But things like samples too, have got inherent variability. And so anytime you take a sample on the bench and try to do the weighing and carry out the sample preparation, of course, there's always variability, associated, with sample preparation. A big problem, that accounts for, most of the irreproducibility. But in this lecture, I'd like us to talk mainly about, the variability associated with all instruments in different, of course, proportions. And that is what you refer to as noise, that is always superimposed, in the signal, that you are getting. Now, ideally, if at all you are to run a chromatogram or possibly even spectroscopy, ideally, this is the type of, output you would like to get. Anytime you are running the blank, ideally you want the signal output to be 0. But when you get a sample, you want the signal, to be very, very large, so that, there's a huge difference, of course, between the blank that is 0 response and the signal, for the sample. But that is a very, idealized, environment, which in almost all cases for all instruments out there actually doesn't exist. In practice, for a fairly good situation, this is what you would get. In fact, you guys, you ran, I think, AAS, essentially that's what you got. You are running a blank, and if you look at your data, it's not 0, but it's got, a response, associated with the blank that you ran. And then when you ran your sample in different, of course, concentrations, you got, an increase in the signal output. So this is an ideal situation where the blank is very, very consistent and it's giving you a fairly reproducible, non-zero output. But again, this is in a fairly good, situation. In real life, actually, this is a kind of situation you get, especially, when you're running data or running samples, over time. Think yourself as an analyst, who works maybe for an environmental company, and every morning, you go to work, you have to run a set of different blanks, samples, and so on, and that's the nature of work you do. And for every blank, that you run every morning, chances are, the data that you get, would keep changing, in the different days, that you are analyzing. And that is what you refer to as drift. And so all instruments, electronic devices, and instruments, of course, are electronic devices, always undergo a bit of drift over time. And so this is a kind of scenario, that you actually deal with as an analyst, in the field. And of course, it's not an ideal situation, and we need to think about how do you solve these kinds of situations, that are gonna, be detrimental, of course, to the data output, that you're producing. And as I said earlier, the data output, that you're producing better be reliable, because in most cases, the stakes can be very, very high. Think of yourself, maybe you've been hired, by a company like Pfizer, to make sure, the vaccines they are producing, have got a certain concentration, of the RNAs or the vaccine active ingredient, that is going out there. And of course, they are producing many doses every day. And you as an analyst, you need to confirm without without doubt that any products going to different kinds of places every day, have got, the allowable active ingredient in them. So you can see the stakes can be very, very high. And so you need to account, for these issues on drift of instruments, that affect, the data authenticity or integrity. And so today we're going to talk about, noise, what it is and what you can do, to minimize noise in the instruments, and I say noise is always there. Now, noise, is, of course, unwanted. You don't want noise, but it's always there. It's unwanted. Noise is random. It's always present, but it's random or almost random. And unfortunately, it degrades the quality of the result. It degrades the signal. And sometimes I like, putting it this way, to differentiate between noise and signal. So noise, is what is coming from your neighbor's, radio, whereas signal is what is coming from your radio. That's what you're interested in. And anything else, is affecting, the integrity of whatever you are analyzing. But every signal has noise, and so it needs to be minimized. But before you minimize it, I think it's very important, for us to discuss how do you quantify noise? How do you quantify how much noise is actually present in the signal? And that's very, very important, of course, before you go into minimizing it. Now, there are two ways of calculating or quantifying noise. It's what you refer to as a peak-to-peak noise calculation, and there's what you refer to as the root mean square noise, which is fairly easily, calculated, as I'm going to show you in the next slide. Of course, noise in an ideal setting, you think of it, as a sine wave, and the sine wave, has got, the crests, and it has, the valleys and so forth. And you can see, it's fairly random, meaning, whatever is beyond zero should be the same as what is, above zero as well. And so if you average, maybe somebody would say the best way to do is to average the noise, maybe between a region. Unfortunately, you would get zero because, if you average noise and it's all random, plus and minus, eventually the data that you actually get is zero. So averaging noise is not an appropriate way, of calculating noise, okay? Averaging the noise or the blank is not an accurate way, of calculating noise. And so an acceptable method, of calculating noise is what you refer to as a peak-to-peak, noise calculation. And of course, it's not very ideal either. So this is where you get, the largest signal coming from the blank or coming from the noise. And then you get the lowest, signal that is coming from the noise. And then you just take the difference between the two. And the difference between the two is what you refer to as noise, calculated as peak-to-peak. Fairly straightforward. Now, however, that is not an ideal way, of calculating, noise either, because you can see that you didn't account, for lots of other noises, that are within, the range of the highest, and the lowest. So an ideal way of calculating noise, is what you refer to as the root mean square, which, as you can see, you know, from the formula here, it's where you just simply calculate, you know, the standard, the absolute, you know, standard deviation of your values. You can see it's an absolute standard deviation calculation of all your blank signals. You can see, you know, that is the amplitude, you know, minus the average noise, you know, which would, of course, would be very, very close to zero in an ideal setting, you know, square divided by n, which is the number of data points, you know, that you are averaging, you know, and then you take the square root of that. And so that's what you refer to as the signal to noise in root mean square, or rather the noise in root mean square. All right. Now, people have realized, you know, the root mean square noise is very, very close, you know, to the noise calculated peak to peak, you know, divided, you know, by 5. So you can actually calculate the root mean square noise simply by taking the noise peak to peak, you know, divided, you know, by 5. And those are the two methods, you know, of calculating noise, where root mean square noise is the best way, you know, to calculate it. Now, of course, you realize, you know, that noise tends to be fairly problematic if at all you've got very low concentration of the sample. Now, in fact, if you look at your calibrations throughout this semester, okay, so you start with the blank, 0, you know, maybe 1 ppm, 2 ppm, and so forth. And that is your signal, maybe absorbance units, let's say, if at all you're doing AAS, for example. Now, you would see if you take the measurement of the blank, and then you take the standard deviation of that measurement, and then you take the standard deviation of the measurement for the 1 ppm, you're gonna see that as the concentration increases, actually you're gonna see the error bars, you know, keep decreasing. The error bars keep decreasing as the concentration increases up to a range, of course. Later on, actually it becomes larger. But within the linear range, within the dynamic range, you know, you're gonna, of any instrument, you're gonna see as you increase the concentration of your analyte, your noise actually goes down and down relative, you know, to the signal, which makes sense. But analytically, you know, you're gonna realize in most cases we are interested, you know, in the very low concentration types of samples. So in most cases, you know, we are pushing the limits of the instrument, you know, to the very, very low range. And as such, noise becomes very, very important, you know, because then it's fairly large relative to the signal in the low concentration ranges. Okay. So in this lecture, I'll mainly talk about, of course, instrumental noise. Remember, we have previously talked a lot about chemical noise. So chemical noise refers to matrix effects. Remember, that's what we have talked about, you know, and the solution to that, we've said the standardization calibration. But today, you know, we are only focusing, you know, on the instrumental noise. And, you know, how do you, we've already talked about how do you quantify it. But remember, there are different types of instrumental noises, you know, that comes from the instruments. And all of them, you know, are electrical. The 4 types, you know, are Johnson noise, the short noise, the flicker noise, and environmental noise. And I'd like you guys to understand the differences between them and what possibly you can do if at all you're an instrument, you know, manufacturer, for example. And I must say, lots of analytical chemists, you know, eventually some of them become instrumental developers. And so you need to understand, you know, some of these things. In fact, if you think about it, you know, your research projects also, to some extent, for some of you, it's about instruments development, you know, because you guys will be fabricating sensors. And so you need to think about, you know, the signal output, you know, the noise that could be present from the instrument, and how can you minimize the noise so that you can enhance, you know, your signal. So the thermal noise, you know, it's one of the most prevalent, you know, noises out there, you know, that comes from the instruments. And so the thermal noise, is caused, by the motion of electrons that are moving within the electrical components, of the instrument. Instruments, comprises obviously of cables. It comprises of capacitors, resistors, obviously, things like electrometers and so on, which is a combination, of all these, types of devices, resistors, capacitors, and so forth. And because all these wires, have got different capacity, conductivities, the motion and conductivity really refers to the motion or the differential motion of electrons across different cables, across different resistors, and so on. And because of that variation, of electron, migration, between all these different types of charge carriers, you get what you refer to as thermal noise, which is dependent, on temperature. As temperature increases, in most cases, the conductivity or the motion of electrons within the wires and the capacitors or within electronic components increases, and as such, your thermal noise, actually increases relative, to the temperature. Now, I should mention, based on this equation, you can see the thermal noise is proportional, to temperature, based on that equation. And you can see that as you reduce the temperature, you, of course, reduce the thermal noise. Similarly, as you reduce the bandwidth, and the bandwidth, is a range of frequencies to which your instrument, is responsive to, equally, as you reduce the bandwidth, you actually reduce, the thermal noise as well. So based on this relationship, you can clearly see how can you reduce, the thermal noise. And you reduce it, by reducing the temperature, reducing, the bandwidth, or the allowable frequency response range of your instrument. And also, you can reduce the thermal noise also by reducing the response time or the rise time, of your detector. By reducing the rise time, of your detector. Because you're going to see, most of the noises, are fairly high frequency. They're fairly high frequency as well. Most noises, they are high frequency noises. And when you have the signal often is a lower frequency signal. So that's a difference, noises are high frequency, whereas, signals are generally low frequency. So essentially you can use the bandwidth, to separate the two. And I've already explained really, what, the rise time is, as I've mentioned. The rise time typically, for signals, is fairly slow, as well. And so you can use the rise time, the allowable rise time, to actually reduce the thermal noise as well. So the other type of noise, that is out there is the short noise. And the short noise, refer to the fact that the movement of electrons, within the electronic devices is not continuous, but instead, it moves in pockets, based on quantum mechanics. Electrons, they move in a quantized fashion. And because of that, you do not get, a very consistent, movement of electrons at any given time. You get pockets, of movement, of electrons, because electrons, by their very nature, they are quantized particles. And so, whereas the current, when you average it over time, is gonna be consistent. At any given time, when you've got electrons arriving at interfaces of different types of electronic devices, maybe diodes, for example, maybe capacitors, maybe resistors and so on. So you've got electrons that are moving, and you've got joints between all these devices, or all these electronic devices. And so you have, the current, being quantized. And so there's fluctuation, because of the movement, of electrons in form of pockets that are quantized. And so for that reason, you get the so-called short noise. And hopefully, it's fairly clear. As you can see from these relationships, short noise is equally proportional, of course, to the charge, to the size of the charge, or of the amount of the charge. It's also proportional, of course, to the current. But I want to highlight, that it's proportional equally, to the bandwidth, meaning, if I reduce, the bandwidth, I equally reduce, the short noise as well. And the bandwidth, I said, is the allowable frequency range by which, your instrument, can respond to. Again, as you can see, short noise is high frequency. It's very, very, very high frequency. Whereas not signal, I said before, is fairly, low frequency. And so again, by reducing the bandwidth, you can actually minimize the short noise. And sometimes they call it quantum noise based on what I've just described. And sometimes, they call it Schottky noise as well, based on the person, who came up with it. Now, the other type of noise out there, and it's very problematic, is what you refer to as, the flicker noise. And the flicker noise is not very clearly understood, where it comes from, but it's very common with certain types of materials. So some materials, tends to produce more flicker noise than others. And so based on that, if at all you're an instrument manufacturer, you would often choose, the materials that experimentally, produce less flicker noise. Unlike thermal noise, which sometimes people call white noise, and short noise, which are proportional, linearly proportional, of course, to frequency, or they increase with frequency. Now, this one is a bit different. The flicker noise is inversely, proportional to frequency. And so it becomes very problematic then, because the flicker noise, tends to be low frequency as well, fairly similar, to your signal. Now, flicker noise is a root cause for this problem. Remember, we called it drift, where you analyze, say, the sample every day, same sample, but you get very different results. Often the flicker noise is the one that is associated with this problematic situation of drift, with the instruments. And again, the solution to it typically, is to choose appropriate types of materials that experimentally have got different or less prone, to flicker noise, which sometimes people call, the pink noise as well. Now, measurements taken, above fairly higher frequency, 1 kilohertz, usually, neglect the flicker noise. So again, choosing the appropriate quieter frequency region to use, can help you mitigate this problem of flicker noise as well. Now, the other type of noise is a so-called environmental noise. And environmental noise, as the name suggests, are things like vibrations happening inside the building, or even, circuits, from the cables in the lighting and so on, that affect the electrical signal from your device. And as you can see in this frequency profile, most of the environmental noise you can see is fairly low frequency as well. And as I've said, before, that the flicker noise tends to be more higher frequency, and you can get a fairly quiet region that you can use, to do or to tune your system or instrument so that you can analyze your samples, within, a certain quieter frequency region. Another solution, of course, to environmental noise is to make sure, of course, you don't have lots of vibration. And so you can put your instrument, on very stable, or what you call, vibration-free tables, vibration-free tables. And you're going to see, if you go to the lab, most of the instruments, particularly, analytical instruments or balances, tend to be on these vibration-free tables so that you can minimize, that idea of environmental noise as well. You can also do grounding, of your electronic devices or instruments, so that you can reduce the noise that is associated with the electric field, within the instrument's room. And so grounding or shielding, is another very common way of dealing with environmental noise. So hopefully you'll be able to enumerate, the 4 types of instrumental noise and ways of mitigating them. It's very important, for this course. And so the next thing that we're going to talk about, is what do you do, to do the enhancement, of your signal relative, to the noise. What can you do? And in most cases, you can do these using hardware, and to some extent I've mentioned what hardware methods you can use, like grounding, and so on. But I like to mainly focus, on the software methods, that you can actually use, to reduce, the noise, which is random, and enhance your signal so that your signal to noise ratio, is fairly large. And so most people, use the software methods of signal to noise enhancement, which are fairly inbuilt actually, in most instruments out there. And that's going to be my focus, in the next short lecture. So there are 4 different types of software smoothing methods that are used to improve signal to noise. One method is a so-called ensemble averaging. The other method is called boxcar. You also have the polynomial data smoothing, and there are different variations of doing that. There's also what you refer to as Fourier transform, filtering, and so on. And so you're going to talk about each one of them in the next slides. Now, ensemble averaging essentially just means that, you take data points and you average them and you get an enhancement, in your signal. Now, ensemble averaging essentially means that, you analyze something, or a sample multiple times, and then again, as I've said, you average them. Now, it's important to remember, that noise in itself, like we said, it's random. Whereas, the signal, should be largely or theoretically the same, in our measurements, whereas the noise is random. Now, if you average multiple signals, essentially the signal intensity should increase proportional to the number of measurements, that you have ran, and so-called N. On the other hand, if at all you run multiple times, the noise on the other hand increases proportional to the square root, of the number of measurements. And so if at all you've got the signal, like I've said, signal is equals to n, multiplied by the S1, so that's the number of, so that's only one sort of, signal or one run. Noise, on the other hand, as I've said, is proportional to n, the root of n, and then multiplied, by the noise, for that one scan. And so if you take the ratio between this and this, to give you, the signal to noise, meaning you take this signal, equation 1 divided by equation 2, you get this relationship. And of course, you can manipulate it, to get this relationship where signal to noise, of n, the number of measurements, is equals to the root of n multiplied by the signal to noise of just a single scan. Okay. And so based on that, then, you can increase, the number of, or rather the signal, by just simply increasing the number of scans, based on that relationship. And I hope that's clear. Now, one requirement, for ensemble averaging is that the data needs to be very, very reproducible. And a good example is with the Fourier transform infrared spectrometer, where if you run only a single scan, and this is real data, if you run a single scan, that's a kind of, spectra that you get. If you run, and you can see the spectra that you get, really, it's just noise, just a single scan, it's noise. If you run 50 scans and average them, now you can see that you're getting some fairly clear, signals in your spectra. Take a look at this on the other hand. If you run 200 scans and then average them, you can see, the kind of data, that you're getting, now the signal to noise is very, very large. And so, you can see the signal to noise is very large, when you do multiple scans, based on this relationship. Now, as I've said, one requirement of the data set, when you're doing ensemble averaging, is that the data needs to be perfectly reproducible. Meaning each of the data points, for your multiple runs, I should be able to take them and average them. Take the data sets that are repeated, maybe 50 of them, and average them into one data set. So essentially you're saying the spectra, should be perfectly reproducible. Now, you're going to see most of the instruments out there, however, do not give you a perfectly reproducible data set. There's always a bit of drift, with your instrumentation, especially certain types of instrumentation. And so ensemble averaging is not usable essentially for all instruments. For example, now if at all you've got, HPLC that you guys are going to do, in the lab, if you look at the chromatogram that you get for HPLC, and x-axis is usually time, that is a signal. If you run it one day, typically you get peaks that look like that. If you run it the next day, sometimes you get slight shifts, in your retention time. And so based on that, then, you cannot really use things like ensemble averaging for data, instruments, that give you shifting, shifting data sets, okay? But like I said, for Fourier transform infrared, because of a component in the instrument called Michelson interferometer, and you guys can check on it later. Michelson interferometer, which is a component in FTIR. Essentially, you are able, to do perfect overlaps, because the data start at the same time and ends at the same time, and so you get perfect, perfect results, that are completely reproducible, and so you can just simply do the ensemble averaging in that case. So very useful, for Fourier transform infrared spectrometer. Now, of course, you can also use it for the so-called Fourier transform Raman spectrometer as well, and we're going to talk about Raman in class. Again, it has a Michelson interferometer, which makes it possible for you to get perfect reproducible results. Now, you can also use it in mass spectrometer as well, and we're going to talk about it in class as well. With mass spectrometer, you can also do you can also do ensemble averaging, because you can fairly get, reproducible results because of especially the time of flight. Mass spectrometer, you can get multiple reproducible results, and so you can do ensemble averaging. Now, the other type of smoothing technique, is the so-called boxcar averaging, and very, very common, like with the HPLC actually is very, very common. Now, in this case, you've got data set, that looks like this, for example, and, of course, the data set, would look like that. And the way the boxcar averaging works is by imagining that any small fluctuations, within, say, a chromatogram are because of noise. All right. Again, we say noise is fairly high frequency, and so we are saying every multiple fluctuation or very small fluctuations within a small region because of noise. And so because of that, you can average out, those data points, that are varied, and average them, to a single data point because of the assumption, that any of the small fluctuations, in the signal is because of noise. And so based on that, then, you would get, say, these 5 data points, all right? And then you average it, into one data point, and that's what you are calling a boxcar. So you take those 5, say, data points and average it into one boxcar. Take those data points, and average it, into one boxcar and so forth, all right? So typically the way it works is, you take, say, the first 5, average it into one. And then you take, not the next 5, but you skip the first data, and then you average those, into one. And then you skip the third one, you average the next 5, into one data point, and so forth, okay? Now, well, it's very good, for smoothing the data, meaning if at all I had data like that, I can now smooth it into something like that looks fairly good. So it's a way of cheating, really, for the data to be fairly good like that, so that it's easier to do integration of those peaks. It's easier to do integration, of a smooth peak than to do integration, of a rugged peak, okay? And so for that reason, you get, it's a way of data smoothing, to remove, some of these noise. Now, the problem is that you tend to lose information, in complex signals. For example, if at all you are running UVV spectrometer, chances are, for a compound such as rutin, which is an antioxidant, or a polyphenol, which you're going to do next week, chances are you can have something that looks like that. When you're smoothing, though, it may assume that this is not a signal, but instead, it's noise. And so when you smooth it, using boxcar, it can give you just a peak like that. And you can see based on that, you'll be losing very, very useful information. So for very complex data, one big disadvantage, of boxcar is that you'll be losing some important character in the signal that can be very, very useful for qualitative analysis especially. But again, it's a very common way of smoothing, very, very common in HPLC and so on. And I'm going to show you in the lab, when you start using the HPLC system, for example. Now, the other method, for data smoothing is a so-called Fourier transform digital smoothing or digital filter. And the way this one works is the fact that, most of the data, especially most of the spectrum out there, is in a time domain, meaning you've got the signal or the frequency, as a function, of time. You've got the signal as a function of time. And you can deconvolute, these time-based spectra into a frequency-based spectra just by multiplying it, with a transfer function. You can convert, a time domain spectra into a frequency domain spectra like that. And so based on that, you would see all the different frequencies, that constitute your signal. And as I said before, most of your signal is, lower frequency, whereas your noise is often, high frequency. And so based on that, you can remove the high frequency noise that is fairly apparent now, in the frequency domain, just often, by multiplying it, with a Boxcar function, that can exponentially decay to remove the high frequency noise. And so you can actually remove the high frequency noise, and you can see you'll be left, with the data, that looks like that has removed the high frequency noise. And then after that, you can multiply, that frequency domain spectra, with an inverse Fourier transfer function to convert it back, into a time domain spectra, that you can see. Very, very common, with NMR, for example, nuclear magnetic resonance, where you convert again, things like the time domain spectra, to a frequency domain spectra. You remove the high frequency noise, just again by multiplying it with a mathematical function with an exponential decay. And then after that, you convert it back, using a mathematical function, an inverse Fourier transform function, back to the time domain spectrum. And that's what I've just explained, in this case. In this case, you can see this is a time domain spectrum. Very busy, very messy. It doesn't seem to be any use for at all analytically. You multiply it by a Fourier transfer function, a mathematical function. You get data that looks like this. Now you can see the frequencies are fairly clear. You're interested, with, the lower frequency. The high frequency is noise. This one is signal. You just multiply this, by a Boxcar-like function with an exponential decay that filters off that noise. And now you are left, with the signal, which you can multiply by an inverse Fourier transfer function to get back, the time domain spectra, which is what you want. So this is actually, the technique, people use for voice recognition in artificial intelligence. You've seen some people, trying to modify voices, so that, say my accent, can be changed into, say another type of accent. And the way people would do is just take my frequencies. I guess mine are fairly low, my low frequencies. And then you would it's a time domain spectra, and then you would multiply, you get the frequencies of that multiplied by a Fourier transform, to deconvolute it. And then, you can change my frequencies, for example, to lower frequencies and so forth. And so based on that, You know, you can imitate, you know, different types of sounds, you know, out there just by doing the convolution, you know, of these frequencies and so on. So again, very useful, you know, these days, you know, for voice recognition, you know, and so forth and so on. So the other type of data smoothing is what you call the polynomial data smoothing. And actually this one is very, very similar really to boxcar. It's very, very similar to boxcar. You know, the only slight difference, you know, is that in some cases, you know, with the polynomial data smoothing, you can apply, you know, a weighting, you know, a weighting ratio on each of these data points. Remember with the boxcar relay, you know, which is not very different, you know, from the 5-point moving averaging, you know, where you take, say, all these data points, you know, and then you average them into one, and then you skip the first one, you know, you average the next 5 into one, and so on. And in this case, it's unweighted. Often the boxcar actually is unweighted, meaning that each of these data points have got the same contribution in terms of you know, being averaged into a single data point. But in some cases, you know, you can have, you know, polynomial data smoothing, you know, where some of these data points you apply an exponential, say, decrease, you know, in the weighting, you know, of that data, okay, such that it doesn't account, you know, for the same weighting. And so in that case is what you call polynomial data smoothing, possibly, you know, with a weighting, you know, average, you know, based on a polynomial relationship like that. But again, very similar to boxcar, the challenges are the same because you're averaging data points and assuming small fluctuations within the data region is because of noise. And so you're smoothing them into one data point. They tend to distort the data if at all you've got complex, you know, complex data. So you distort the data and lose information, which is a bad thing when you have complex data. But again, you know, they help, you know, in smoothing the data so that you can easily integrate, you know, the results. If at all you have a smooth curve, it's easier to integrate the results. So if I may show you, and I think I've tried to sketch it, you know, in my previous slides when I'm explaining, but it's a little bit messy. You know, your data, in most cases, you know, say your time domain data, you know, look like this, you know, the gray data that I have there. Now, again, you can see it's very, very messy, but often that's the real situation. That's the real raw data output, you know, that you get. Very difficult, of course, you know, to integrate and so on. If you apply moving average smoothing, for example, polynomial data smoothing, or even boxcar, you know, you can see now you get, you know, these red, you know, you get the, sorry, you get these green, blue, you know, type of peak. It's much more smooth. It's a lot easier to integrate. Take note of this, you know, because it accounts also for the fact that, you know, you can do ensemble averaging. If at all you've got multiple data points, you know, again, it's fairly easy, you know, to increase the intensity, you know, of your peaks and so on. You know, so again, it's a way of making the data, you know, look fairly good. Lastly, it's important, you know, to remember that the data set that I've shown you here, you know, comprises telling the instrument how many times I should actually acquire my data, how many times, you know, I should detect my signal, how many times the detector should respond. So all these, you know, really are data points, you know, that are used to create, you know, these spectra. So the question is, how many times, you know, should I actually tell my detector, to acquire the data points. What's the maximum, what is the minimum? Now, ideally, of course, I want enough data points so that I can construct, my signal in an authentic way. But you can acquire too many such that it becomes computationally heavy, and then, your instrument or your software, keeps freezing, because the data set is just too big. So the question is, you need to assess when you're developing the method, how many times, should you acquire, your data, should you instruct your instrument to acquire your data. And in fact, we're going to see this, when you're doing your, especially your electrochemistry, we're going to tell the method, or when you're building the method, you're going to put in the number of data points, say you want, possibly in a certain time region. So it can be too little in this case, or it can be too much, where you got too many data points, that make it difficult, to do your, to store your data. And so we use typically what you refer to as the next criteria to determine the least amount of data points, that you actually need to construct, your signal. And based on the next theory, next criterion, this equation here, it says, that you need essentially at least two data points, per region, assuming, of course, your data is a sine wave, and often that's how we visualize data as a sine wave. You need, two data points per period, and that's a period, two crests make a period. So you need two data points, per period, to construct, your time domain spectra. You need two data points per period. However, of course, two are too little because you'll be losing information if at all you've got complex data as well. So often we acquire not just two, often we acquire, more data points, per period, so that you are able to fully construct, your data set. But again, the minimum instructed based on the NIST criterion, it would be two data points per period.